Okay, well, very good morning, students. Today we are going to see torque about an axis. Suppose we take a body is moving in an anti-clockwise rotation like this. The body is of mass m. A force is applied on this body as shown tangentially. So this is a tangential force. The distance from the axis of rotation of a mass is at the distance of r. So the r vector is directed in the direction of f vector here. Because of this tangential force, the body is moving in circle about this axis, that is a dash, and it is defined as that is tau is equal to tau a dash is equal to r vector cross f vector into n cap, where n cap is a unit vector along the axis. So which axis is here? A and a dash. So right hand thumb rule, if I extend the vector r like this is the r vector, that is r cross f by right hand thumb rule gives you torque. So if we have the side vector as r, this is vector f, use your right hand and stretch the fingers of right hand from here r cross f. So thumb will point in this direction. So this is the direction of torque tau. So torque is along the axis a dash. It is an axial vector. So the direction of the n cap is a unit vector along the axis a dash. So therefore we called torque is along the axis. It is an axial vector, that is r vector. So r cross f is equal to tau by right hand thumb rule. In this diagram, the force is a tangential force, that is r is the radius vector. Then we will write torque is equal to rf sine theta n cap. So the direction of force which is tangential and the radius vector r are perpendicular to each other. So the angle between theta is equal to 90 degree. So magnitude of torque will be rf. What is the force? F is equal to on body of mass m, and it will be mass into acceleration, that is a means what? Tangential acceleration. So into r distance, the distance from the axis of rotation, this can be written as m. Tangential acceleration is simply written as mr square alpha. And mass, which is the distance of r, we write it as mr square into alpha. So alpha is the angular acceleration about the axis a dash. We know what is mr square, the product of mass in the square of the perpendicular distance from the axis of rotation. I is the moment of inertia. So alpha is the angular acceleration. Okay, now let us see what is torque. So to have torque, we need a tangential force and a offset from axis. So there was an equation, tau is equal to ftr, that is T is torque and Ft means tangential force, and to the distance to axis, or sometimes called the radius of distance. Okay, so in my torque equation I can put matrix equation, okay, tangential force. And now let us see what is acceleration. So force causes acceleration. So Ft is equal to mat, that is mass times the tangential acceleration. So this is tangential force and this is mass and this is tangential acceleration. So in my torque equation I can put mass into tangential acceleration in the place of tangential force. Okay, so in the first equation, that is tau is equal to mat into r. So when the relation between the tangential acceleration and the angular acceleration, that is at is equal to alpha r. Okay, so at means tangential acceleration and alpha r means angular acceleration. So times the radius, or a radius is the distance to the axis of rotation. So now I am substituting this, that is tau is equal to m into alpha r into r. Now I am going to rearrange this. Okay, so now I am going to rearrange this. So tau is equal to m into alpha r into r. So tau is equal to, if I am rearranging this, so tau is equal to mr square into alpha. So I could have more than one torque acting. So okay, in this case I need an net torque. So I want some other torque, that is net torque in angular acceleration. So I is equal to mr square. So that is I means what? Moment of inertia. So sum of the forces cause linear acceleration. Here torque for the rigid body can be written as tau is equal to I alpha. So the final equation is torque, that is torque is equal to moment of inertia into angular acceleration. Now let us see what is angular momentum. So angular momentum in rotational motion is equivalent to linear momentum in translational motion. So the angular momentum of a point mass is defined as a momentum, that is moment of its linear momentum. In other words, the angular momentum L of a point mass having a linear momentum, it is denoted by L, and the angular momentum of a particle is minus L is equal to R into P. Okay. So if you look at the relation between linear velocity and angular velocity and linear momentum and angular momentum or force and torque, everywhere you see the angular component is equal to the cross product of position vector and the linear component. So L is equal to R into P. This is the linear component. So L is equal to RP sin theta, where theta is the angle between R and P. And so here you can see the linear velocity and angular velocity. So linear velocity is what? V. V is equal to omega into R. Okay. If we are taking the relationship between torque and force, so tau is equal to R into F. If you are taking angular momentum and linear momentum, L is equal to R into P. So L is equal to RP. This is what? Angular momentum. So that is relation between angular component and linear component is a cross product, and the cross product is with the position vector. So everywhere except the linear component and the angular component, the third quantity present is the position vector. So in this case, the magnitude of the angular momentum RP L is equal to, that is RP sin theta. So which is theta is the angle between R and P, that is position vector and linear momentum. Okay. Now let us see the relation between torque and angular momentum. Okay, now let us see the relation between torque and angular momentum. So that is angular momentum L vector is equal to R vector cross P vector. So the cross product of the position vector and the linear momentum. Okay, so differentiate on both sides. So what we will get, dl vector by dt is equal to, here d by dt into r vector cross p vector. And again if we are differentiating this r vector and p vector, so we will get dr vector by dt into p vector plus r cross, okay, dp vector by dt. Okay, so this is a differentiation of r vector cross p vector. Okay, now we can write this dr vector by dt. Okay, so dr vector by dt as v vector into p vector plus this we can write as it is r cross dp vector by dt. Okay, and next v vector cross p vector, that is mv, p vector is equal to mv, so mv vector plus r cross dp vector by dt. Here v cross v vector cross v vector is equal to v into v sin theta, so theta will be 0. Okay, so theta will be 0, so we can put 0 here, 0 plus r cross, that is r into dp vector by dt. Okay, so from Newton's second law we know that dp by dt is equal to f. Okay, so here dl by dt is equal to r cross, that is f, because by Newton's second law we know that dp by dt is equal to f. So dl by dt is equal to what? R vector cross f vector, so which is equal to tau. So we defined it sometimes back, that is dl by dt is equal to tau. So time rate of change of angular momentum is equal to time. Okay, now we are going to see angular momentum and angular velocity. So what is linear momentum? P is equal to mv. Okay, so P is equal to mv, that is P vector is equal to m into v vector. Okay, next we have to find what is angular momentum. So angular momentum, the equation of angular momentum, that is L is equal to I omega. So here instead of mass we are putting I. Okay, that is moment of inertia. So now let us consider classical equation. How we define classical angular momentum. Here this r is here and the mass is m and the momentum of mass is what? P. Okay. So we can write L is equal to r vector cross P vector. So the moment of P is in tangential. Okay. The radius is in normal. Okay. So that is what? 90 degree. So the angle is what? 90 degree. So how we can write this? Okay, how we can write this? L is equal to RP sine 90. Okay, so modulus of L is equal to RP sine 90. So which is sine 90 is what? 0. So which is equal to RP. Okay, so this is what? Linear momentum. So instead of P we can write mv. So RMV. Okay, so P instead of P we are writing mv, and then instead of V we are going to substitute, that is V is equal to R omega. This is angular velocity we know. So which is equal so here L is equal to mr square omega. So from this we can know the mass at this point axis which creates momentum. So that is mr square omega, which is I omega. So mr square we can't write like this because the blue color, see this diagram, the blue color indicates the rigid body that revolves, that is mr square means which has the different mass and different radius. Okay, so first we have to find what is I. Okay, so I is equal to m1 r1 square plus m2 r2 square plus and so on mn rn square. So how we can write this? We can write summation of m r square and 1 to from 1 to n. Okay, so this is the angular momentum. So the angular momentum is what? L is equal to I omega. Okay, so we can write this I. Okay, so this is I omega, where I is a moment of inertia and which is equal to the mass. So this is the angular momentum. We find that angular momentum of equation. Now let us see the next topic, equilibrium of a rigid body. So what is a rigid body in equilibrium, and when will you say that a rigid body is in equilibrium? So a rigid body is said to be in mechanical equilibrium. Okay, so when total force on the body is 0 and total torque on the body is 0. So what happens due to force? Force causes translational motion, and what happens due to torque? Torque causes rotational motion. Okay, so when both the causes of the motion are 0, that is the object will be at equilibrium. Now let us take the example. Have you all seen the flying disc? Okay, which you often playing with it. If you held the flying disc, if you try to balance with your finger, what happens? Sometimes it toggles down and sometimes it falls down. So things like that happening. Okay, but if you balance at the correct point, at the exact point, okay, then it gets balanced and it doesn't move at all. Okay, so at that point of time we see that the flying disc is in equilibrium, that is the total force is also 0, because of which there is no linear motion. So the total torque is also 0, because of which is there is no angular motion or rotational motion. So in case of rigid body, also we see that it is a mechanical equilibrium when total force as well as total torque both are 0. So this we can put it mathematically. So when I say that the total force on the body is 0, that is summation of Fi is equal to 0. So summation of Fi along the x-axis is equal to 0 and summation of Fiy along the y-axis is equal to 0 and summation of Fiz along the z-axis is equal to 0. The force, the components of force along x, y and z direction are equal to 0. Again, if I say the total force, that is the total torque is 0, that is summation of a total torque, that is torque tau I is equal to 0. So summation of torque x along the x-axis is equal to 0 and along the y-axis is equal to 0 and along the z-axis also 0 for a rigid body to be in equilibrium. So these 6 mathematical equations should be satisfied. Okay, so now these equations are 0, then we said a rigid body is in mechanical equilibrium. So partial means something that is now let us see partial equilibrium of rigid body. Okay, so partial means something which is not complete. Okay, so that is the rigid body is not completely in equilibrium, but it is partial in equilibrium. That is, a body is said to be in partial equation if a body is said to be in partial that is equilibrium if it is in translational equilibrium and not in rotational equilibrium. Okay, so translational equilibrium means the net force is 0. Okay, so the total net force is what? 0, and it is not in rotational equilibrium. That is, net torque is not equal to 0. So in this, total force is 0, but total torque is not equal to 0. So it is in rotational equilibrium and not in translational equilibrium. So here total torque is equal to 0 and total force is not equal to 0. Okay, so in the previous I said that two conditions, okay, right, for equilibrium. If any one of the condition is true and one of the condition is false, then we say that the body is in partial equilibrium. So now let us take the example of both the cases as in scenario. So the body is in translational equilibrium and the body is not in rotational equilibrium, and in other scenario the body is in rotational equilibrium and not in translational equilibrium. So let us look at this example of the first scenario. See that the body is in translational equation. The total force is 0, that is summation Fi is equal to 0, but summation, that is torque, is not equal to 0. That is the first case. Okay, now let us suppose we have a rod. The force F1 is applied in this direction and we apply equal and opposite direction, that is F2 in this direction. Here we see F1 is equal and opposite to F2. So there are equal in magnitude and opposite in direction. Therefore the net force is equal to 0. But these forces are acting along the different lines. Okay, so this causes the rotation of this object. So total, that is torque, is not equal to 0. So this causes rotation and therefore the object is not in equilibrium. Okay, so similarly let us take another example. Suppose the body is in rotational equilibrium. Okay, so what will happen? So torque I is equal to 0, but total force, that is summation of Fi, is not equal to 0. Now let us take the example of same rod. If I apply the force F1 here and I am applying the force F2 here, maybe both are of in same magnitude but they are both along in same direction, that is total force, that is total force is not equal to 0. Now since we are applying force from both the ends, as a result what happens? The rod will start coming down. Okay, so as a result translational motion will take place. However, there will be a rotation involved. So the net torque in this case is 0, but the net force is not equal to 0. Okay, so as a result the rod is not in equilibrium. So the rigid body is completely equilibrium only when the total force is also 0 and total torque is also 0. Thank you. Now let us see types of equilibrium. So what is equilibrium? So equilibrium means everything which is balanced. If an object is said to be equilibrium, so the object is at rest. Okay, so that is, it is balanced everything. Now let us see translational equilibrium, types of equilibrium, and we are seeing first translational equilibrium. So what is meant by translational equilibrium? Sum of all the external forces acting on the object equals to 0. And here linear momentum is constant. So what is linear momentum? The product of mass into velocity. Okay, so that is called, for moving object, the product of mass into velocity for moving object, that is called what? Linear momentum. So linear momentum must be constant and net force is 0. Okay, next rotational equilibrium. So what is rotational equilibrium? Object moves in a rotation about an axis. So here angular momentum is constant, net torque is 0. So angular momentum is what? Mass into radius into velocity. Okay, so and third one is static equilibrium. So static means not moving. Okay, the object doesn't move. That is called what? Static equilibrium. So here linear momentum and angular momentum are 0 and net force and net torque are 0. Okay, next dynamic equilibrium. So dynamic equilibrium means rate of forward reaction is equal to rate of reverse reaction. Okay, so linear momentum and angular momentum are constant and net force and net torque are also 0. Next is what? Stable equilibrium. So stable equilibrium means when the ball is kept at the bottom of the bowl and if slightly moves the ball, what happen? It goes some distance and come back to the original position. So that is what? Stable equilibrium. So linear momentum and angular momentum are 0 and the body tries to come back to equilibrium. It's slightly disturbed and released. The center of mass of the body shifts slightly higher if disturbed from equilibrium, and potential energy of the body is minimum and it increases if disturbed. Next one is unstable equilibrium. Unstable equilibrium means if the ball is on the top of the sphere, okay, so we can't know where the ball will move, okay, so it never come back to the original position. So linear momentum and angular momentum are 0. So the body cannot come back to equilibrium. It's slightly disturbed and released. The center of mass of the body shifts slightly lower if disturbed from equilibrium. And potential energy of the body is not minimum and it decreases if disturbed. Okay. Next one is neutral equilibrium. So neutral equilibrium means when the object is moved slightly, that is linear momentum and angular momentum are 0, the body remains at the same equilibrium if slightly disturbed and released. So the center of mass of the body does not shift higher or lower if disturbed from equilibrium, and next potential energy remains same even if disturbed.